Hi everyone. Element 14 recently selected me to review a new step-down buck converter that they have on offer. It's a Richtek, I hope I'm pronouncing that correctly, RT7275GQW. It's an evaluation kit, and it's a voltage regulator that claims extremely good stability on the output. It can run at up to 3 amps on its output and can take anything from about 5 volts to 18 volts on its input, and can supply an output of about 700 millivolts right up to about 8 volts by adjusting resistor divider network on its output. It's an extremely small board. I'll show you that in a minute because I've got it hooked up to a test circuit right now, and it has a lot of really good claims like fast response time, automatic current limiting. It's supposed to be very efficient and has a minimal component count. So if you were going to include it on one of your circuits, it would theoretically have a minimal bill of materials to implement it. So, you know, without any further ado, let's get into having a look at what the board is and how we are going to hook it up and test it. Okay, so this is the board. The actual RT275GQW is this tiny chip right here. This is the inductor for the output. As I said, it's a buck converter. Down here are a couple of resistors that are the divider network for the output, and you've got your input volts coming in here. As I said, up to 18 volts is the maximum it can come in. On the other side here is the output, which can go up to about 8 volts on its maximum output. So I guess this thing's really designed for sort of a 3.3 or 5 volt kind of regulator. And it says that it can do 3 amps, so we're going to crank that up. And it says it also has very fast response time, so we'll give that a test as well, because what I'm going to do is I built up a little DC load that I'm actually working on for my bench power supply project, and I actually have a high capacity load generator capability that I can actually plug into my Agilent signal generator. So we'll throw in some high frequency, low frequency load changes at it and see how well it performs. Let me just pull out the data sheet and we'll show you a few things. Okay, this is the feature list we're looking at now, so let's just quickly go down this and see what it has to say. So fast transient response time. So by this, it typically means that if you have a quickly changing load, it is able to keep up with it and keep the voltage output within limits of what you've programmed it to be. So we'll give that a test. Steady 700 kilohertz switching frequency at all load currents. I'll see if I can get an oscilloscope hooked up into the input to the inductor, and we'll see if it actually maintains that 700 kilohertz. 3 amp output current, so we'll test that as well, and what we'll do is we'll vary the input from its minimal to its maximum and see if it holds that output current. We'll also, while we're doing that, see how efficient this thing runs. Advanced constant on-time control. So if I can figure out what that is, we'll look into that too. Optimized for ceramic output capacitors. This is basically trying to get your bill of materials down so that on the board you'll just have these surface mounts, not have to have electrolytics or tantalums or anything like that. 4.5 to 18 volt input voltage range. Sorry, I was overestimating slightly, I think. Anyway, so 4.5 to 18 volts on the input range, and we will test that. We'll see how low we can actually go, see if you can actually take it below 4.5 volts. This thing comes out of the box programmed to give out about 1.05 volts, I think, or just a little bit over 1 volt anyway. So we'll test, see how well it manages to maintain that. Internal 90 milliohm switching and 60 milliohm synchronous rectifiers. Well, I don't think there's much we can do about checking that except to see if this thing gets very warm. I think one of the things that you will gain by having very low switch on resistance though, and flyback rectifier resistance, is that you will have a smaller margin, so a lower dropout between your input and your output. So we'll see what we get when we actually start testing that. Output 0.765 volts to 8 volts adjustable output voltage. The adjustment on the evaluation board, it would have been nice to have a 10-turn pot on there or something like that so that you could program it, but no, they've put in a couple of preset resistors, and they're tiny surface mount ones. So we'll have to see if we can figure out a way at the end of the video to see if I can actually change the output to something more useful, like, I don't know, 5 volts for an Arduino or something like that. Externally adjustable pre-biased compatible soft start. Well, okay, we'll take their word for it, but we'll, if we get time, we'll look into that. Cycle by cycle current limit. So cycle by cycle means that it should be a lot quicker to respond to current limit changes. So if you suddenly draw more than 3 amps, it should be able to come down, cycle down. But then if if it was a very quick overload, as soon as that overload goes away, it should recover extremely quickly because it's cycle by cycle. And typically when they're talking about the cycles, they're talking about this 700 kilohertz switching frequency cycle. So within the period of one cycle to the next, it should be able to continuously adjust its constant current output. So there's a few things in here that we're going to test. I mean, if ultimately people are going to want to use this for powering their Arduino or other projects. So the key things they're interested in is how efficient is it? Can it deliver the power that it claims it can deliver over a wide input voltage range? And can it run cool? And how much noise is on the output? And how quickly can it start up? All right, so we're going to have a look at trying to test all of these things and see what it does. So let's get back to the circuit and start getting things hooked up. Just want to quickly go over the schematic before we actually start playing with the circuit. So what we've got, this is the schematic that's provided with the documentation online. We have our input volts here. We've got 2 10 microfarad smoothing capacitors on the input in parallel along with a 0.1 mic. So that's giving you a reasonable range of frequency filtering, noise filtering on the input, and then that's fed straight into the chip. We have a jumper on the board, and if you connect this between the enable pin, which is pin 2 of the 3-pin jumper, to ground, it turns off the buck regulator, and if you connect it through this 100K to the plus rail, it will turn on the buck regulator. This capacitor here, 3.9 nanofarad, is for the slow start capability, and there's a test point provided on the board so we can have a look at that kind of ramp. I'm not sure how much it's going to tell us anything, but we can have a little probe with the scope later on. We've got the SW output across the top here, which is connected to our 1.4 microhenry output inductor. The flyback diode and the actual switch is both built into the switching regulator, and we have a feedback here for R23 and R28, so we have an 8.2K and a 22K divided network. This C30 is not fitted, so it's just these 2 resistors feeding back to the feedback. So later on I'm going to see if I can maybe replace this 22K here with a 50K pot or something like that, so we can actually adjust the output dynamically. I mean, it's right now it's 1.05 volts output, so even if this was a 10K, that would be more than enough to try this. It just depends on what pots I've got. And then on the output, we've got these 2 22 microfarad caps and another 0.1 microfarad to provide output noise filtering, and then that goes straight out to our output terminals. You've got another output from the regulator, which is PG, which is for power good, and that's a test point as well. And if you were using this with a microcontroller, you could use that one to actually inform the microcontroller that it's now got enough supply that it could start up or something like that. And I think that's pretty much it as far as the relevant pins are concerned. You can have a look yourself online and look at how the internal functionality, pull the data sheet to the actual switching regulator to see the other features that it may have and things. But as far as its basic functionality, that's really it. The data sheet that comes with this from Element 14.2 includes the complete bill of materials. So if you wanted to build your own board, there's everything there that you need. And obviously, it tells you how you can adjust. There's some board schematics for this one. I'll go back to the actual board layout in just a moment. And the other thing that you've got here is a list of all the pins and the test points that you've got to play with. So the PVCC, which is one of the other pins, that's the linear regulator output test point. All right, which is internally, it's a linear regulator output, which is 5.1 volts. So I guess that's what it uses for its internal circuitry. Power good connected to PVCC through an R29. Power good voltage is 5.1. So when soft start is complete, the output voltage is in regulation. Anyway, so I'm not going to go through all of those. I've already spoken about a few of them. Output voltage setting down here. Let me just slide this up a little bit. Just here. So what it says here is that the output is 0.765 volts, which must be the minimal output you can have, which is what we saw in the data on this sheets earlier, multiplied by R23 over R28 plus 1. So that's a standard resistor divider network. And you know, if this ends up being 1, then you know you're just going to get your twice this voltage. If you know, so basically if you mess around with the R23 and R28, and we'll look at some calculations later, we'll be able to adjust it and we'll see if we can get 5 volts out of this thing and see how well it works there. The output capacitors are rated at 16 volts, so you know it says do not exceed their range, but basically this thing is supposed to only have a limit of 8 volts on its output, so hopefully you know you won't be able to just adjust those resistors and get more than that anyway. Although technically, because it's a buck synchronous regulator, you could, maybe if you had some fault condition, the input connected to the output, you know, it could happen. That's pretty much it of relevance in this thing. And so let's get back to the board and we'll start doing some testing. Okay, what I'm holding here is my FET-based DC load. So what it's got is basically a high-powered FET that can handle, well, tens of amps, a 0.1 ohm temperature-stable sense resistor. Underneath it is an actual 1 ohm sense resistor as well, but I don't have it hooked up for this because the output of this thing is just over 1 volt, and the current is 3 amps. So you know, with a 1 ohm resistor, you wouldn't actually be able to get this thing to output its full current. So what I've done is I've just tapped in a 0.1 ohm resistor so that we can actually get the full current or more loaded on this thing with the rated 1.05 output volts that it's pre-programmed to do. I've actually coupled a couple of resistors onto the wires onto the output of this board. If I just disconnect my meter for a moment, I've soldered these on the bottom and then tapped them into the wires that I had for my DC load, because you know, with it's such a low voltage, I didn't want to just have simple clips, because any resistance at 1 volt, you know, even just 100 milliohms or 50 milliohms, is going to make a difference on how many amps we're going to be able to draw out of this thing. So I soldered this directly and soldered it straight to the FET for the load. So let me just reconnect this. So what I'm going to use is I have a Keithley bench power supply, which is supplying right now 4 volts on its output, and I'm using the second output. It's a triple output power supply. The first output is providing the input to the Richtek DC to DC converter. The second output is actually used for the gate voltage of the FET, because I don't have a proper control circuit built yet. As I said, I'm busy doing some designs for the bench power supply project, which is a modular system, and my next videos is about the output stages. So I haven't yet integrated the feedback or anything, so I'm just directly controlling the gate from a second output of the power supply. And then what I've got down here is my 2 meters that are going to monitor the current across the 0.1 ohm 1% sense resistor, and I'm going to be measuring the output voltage to see if it stays stable. And then a little bit later on we'll hook up the scope to see what kind of frequency is coming out of this thing, if anything, on the noise and stuff like that. So I have this hooked up right now. The gate voltage is set quite low so that it doesn't show anything. I'm just going to zoom out a bit so that you can see all of the circuitry. So we have the output of the power supply set to 12 volts, which is the nominal voltage input for this Richtek DC to DC converter. We've got 0 volts set on the gate, so the my DC load will be completely turned off right now. And as you can see on the meter here, there's 0 millivolts across the sense resistor. So the output is now stabilized at 1.047 volts. So I'm going to write that down. We're going to keep track of things. So 1.0475 volts at 0 amps. So I'm going to start taking the gate voltage up until we get to about 100 milliamps of load, and we'll see what we end up with there. Probably have to go up to a couple of volts before we get anything starting to show. So excuse the arm right now. We have about 2.3 volts, 2.4 volts on the FET. We're up to about 185 microvolts so far, so it's nowhere near enough. That's equivalent to milliamps. We want to switch this thing so that we've got basically 100 millivolts is equivalent, trying to think, 100 millivolts is equivalent to about 10 milliamps. Sorry, about 1 amp. I'm going a bit coarse here. So just 42, so that's about 420 milliamps. Let's just bring this down. I'm just trying to be a little finer with the control here. We want about 10 milliamps, which is going to equate to, we want about 10 millivolts on here, which will equate to 100 milliamps on the load, because it's a 0.1 ohm resistor. So we'll just get that down to there. Just adjusting the voltage a little bit just to get it as close as I can so we can see what the output voltage is. Alright, it says 1.00, that's close enough to 100 milliamps. So going into this up here, I don't know if you can read it on the screen or not, we actually have about 16 milliamps feeding in to the DC to DC converter, and we have 100 milliamps coming out, and we have 1.0472 volts on the output. So let's crank this up to 200 millivolts, 200 milliamps. So that's got to go a little more coarse than that, I think. 170, 180, 198, 198 and a bit, 210. Let's just drop that down. So we need 20 millivolts across this thing. There we go. That's pretty good. So 200 milliamps being drawn through this thing. We now have 1.0471 at 200 milliamps, and we have 25 milliamps going in. So let's just crank that up again to 300. All right, so 300 milliamps being drawn from this thing, 1.0472, and 34 milliamps going in, and we've got 300 milliamps going out. All right, I'm just going to speed up the video here, actually just cut the video, and I'm just going to go through the rest of the readings until I get close to the top, and then I'll bring the video back in. All right, I'm just about to hit the 3 amp output limit, which will be 300 millivolts on this meter here, and as you can see, the output is still sitting nicely at 1.0475 volts, and I'm just going to crank this up until I get exactly 300 millivolts, which will be equivalent to 3 amps on the output stage. Almost there. Okay, so exactly 3,000 milliamps, well, 3001, and we're drawing 362 milliamps on the input, and we still have a nice steady. So Alright, so that's 3 amps and we haven't current limited and the output hasn't collapsed. So now I'm just going to take it up and see at what point the output decides to shut down. So 303, so 3.03, so a 10% over, 20-30% over. So 3.2 amps and it's still going strong. 3. Got to change the range on my meter here. So 3.3 amps and it's still giving us a nice stable output. Stick my fingers on this thing. It's not warm at all. It's, you know, I can leave my fingers on here and it's, you know, 12 volts down. So, but if you consider it's only drawing 400 milliamps on the input to give us out 3.3 amps, you know, it's not transferring a lot. I mean, it's 12 volts. We'll do the math in a little bit, but it's you know, I can feel that it's warm, but it's, you know, I can leave my fingers here all day long. So it's probably only in the region of, you know, 30 degrees, 40 degrees or something. So let's go up a bit more. The output's still staying stable at 1.0474 volts. Oh, the volts just dropped a tad there, 3.35 amps. See at what point it collapses. So up to 3.4 amps. 3.5 amps. Output voltage dropped off a bit, 4.072, but it's only, you know, 0.01%. 3.6 amps, 3.7 amps, still going strong. The output's dropped a little bit, but nothing much significant. 3.8 amps, still 1.046, the output's dropped a bit more. 3.9 amps, 1.068, so it hasn't overloaded and shut down yet. 3.9. So we're at 4 amps on our output now, and the output is still holding 1. Oops, my meter just shut off there. We're still holding 1.046 volts, so it's still staying very much within tolerance. I mean, it has dropped, but it's still good. So 4.04. I expect at some point this is going to actually shut down the output. You know, it should, because it's supposed to be overload protected. 4.1 amps, 4.2 amps, drawing 600 milliamps almost there. It's starting to shut down now. So it's suddenly dropped, so let's just back that off a little bit. 1.04, 1.05, so 426 millivolts, which is equivalent to 4.26 amps. At what point the output has decided to collapse it down. So I'm going to back this now off so that I'm drawing the 3 amps. So that's pretty good. So I mean, it's actually delivering significantly, you know, more than what it said. It called for a 3 amp current limit, but it's actually giving us 4 amps before the current limit is cutting in. So it's got plenty of room over the top, you know, if you're doing this. And this is 12 volts in and 1 volt out. So I'm just backing this down to 3 amps on the output, and then I'm going to start cranking the volts up to see what happens. I've been recording this on a piece of paper as well, so I'm going to put this into an Excel spreadsheet when I'm done. Alright, so here's all the results so far. I don't know if the camera's going to focus on that, but anyway, I'll put these into a spreadsheet and put them in part of the video so you can see it. Alright, so I've now got 3 amps on the output. We're back to our 1.047 volts as well on the output, and we've got 12 volts on the input. So what I'm going to do now is I'm going to crank the input volts up to the full 18 volts and see what we get here. Let's just go across. So it's 12, 13. So 12 volts, it's 3007 milliamps and 1.0474 volts on the output for 13 volts. It's got up to 16 volts. The output's rock solid, 1.0475, and it's still exactly 3008, so it's barely changed, hardly at all. Okay, there's 18 volts. I'm not going to take it above that because I don't want to destroy the chip. Its maximum voltage is 18. It's still happily supplying the 3 amps, and it's still happily outputting 1.047 volts, so that's pretty good. And that's with 18 volts on the output. So now I'm going to go back down to 12 and we'll work the other way. So we've got 12 volts now, we're back to where we were. Now I'm going to go down to 10 volts. So we've got 10 volts. So the output's dropped a little bit, but nothing. 1.047 still, it's 0, and we've still got 3010 amps coming out, and we've now got 10 volts going in. So let's go down to 8 volts. So we got 1.0467 on the output. Still got 3010 on the current, and we've got 8 volts on the input. Now if we back this down to 6 volts on the input, so we're getting close to that minimum, which it said was 4.7 volts for this. So we've still got 1.046, so we're still less than, way under 1% deviation on the output voltage here. It's 1.04 all the time, so we've barely shifted 0.2% or something like that. I don't have to do the math, but you can see for yourself it's very, very little. The current is staying at 301 so that's barely deviated by anything, which in a DC load it shouldn't be changing. I'm now down to 5 volts, and the current is remaining the same, 1.045 volts on the output. Now I'm going to change the resolution of my step down here because I want to bring it down now. So this is 5 volts, so 4.7, theoretically it should start collapsing on the output. So that's 4.7 now, and I don't know if you can see that, but it's still sitting nicely at 1045 on the output. So it still is quite happily kicking out the 3 amps, 3.013 amps, and that's 4.7 volts. Now the one thing you will notice though is that the input amps now has gone up to 929 milliamps. Alright, because obviously, because it's effectively a power transfer, your input current has to go up if you don't have the volts on the input. Alright, so now let's start cranking this down until this thing gives up. So we're at 4.6, 4.5, 4.3, 4.2, 4.1. Alright, so this had a 4.7 minimum. We've still got 3.99 volts, and we've still got coming out of this thing 1.045, which is still exactly what it was when we had the higher input voltage. So this is doing pretty good, and the current is still being maintained at 3014, so easily within spec of the current range as well. Of course our input current is now up to 1.117 amps, because less voltage in, you've got to have more current going in to get the same voltage and current going out. So we still haven't collapsed this thing. Let's go down a little further, and we'll just keep going this time till it collapses. There, just collapsed. So 3.7 volts is where it actually gave up. If I just take this back up a bit, there. So it seems to have a tad of hysteresis. 3.8, 3.7. Yeah, as soon as it went to 3.6 volts on the input, it failed. So 3.7, it was still maintaining its output. I'm just going to take that back up again. Let's just try that again. 3.7 on the input. So it's sitting there at 3.7. It's giving out 1.058 still. 458, sorry. And it's still delivering 3.013 amps. at 3.7 volts. So if I just take that down that one click further, and the output now switches off because your input is no longer able to, the voltage drops across the regulator and everything are no longer able to generate that output. So that's pretty impressive. This thing, it's exceeding its, from a voltage regulation perspective and things like that, it's actually exceeding the quoted specifications quite a bit on the output current, on the input voltage range. I'm not going to exceed the input voltage range, like I said, because I don't want to damage it. But it certainly seems to be able to supply more current than what it says. It's keeping its output, it's extremely stable across the complete range of input volts and across the output volts. So if I leave this thing, I'm just going to take it up to maybe a 4 volt input now, just to see what it's going to do. So I've got the 1.045 output again at 3 amps. So I'm going to see if I can increase this current to take it to its maximum, see where it collapses with the minimal input now. So 3.2 amps, 3.3 amps, 3.4, 3.5, 3.6, 3.7 amps, 3.8 amps. There, just started to collapse. I think it's right on the brink there. If I back it off a little bit, it's probably going to come back and stabilize. Yeah, so 3.8 amps with a 3.4 volt input. It's drawing 1.5 amps in. It's outputting 3.8 amps at 1.044 volts. So even at the lowest input, it's able to maintain that output and provide a lot more current. Now probably it's getting a tad warm now, I'd imagine. And sticking my fingers on is affecting it, but I can actually feel now this is working a little bit extra to try and maintain this, because obviously it's having to switch 1.5 amps now instead of the 100, 200 milliamps that it was switching when it had a higher input voltage. In fact, it's probably going to shut down on me if I let it get any hotter, because the it's too hot to leave my finger on now anyway, so that's getting quite hot. I think I've got I don't know if I can tell with this cheapy temperature probe, but we'll have a look, see if we can actually see what it's giving us. So that's about 45 degrees, 44, 46. It's not exactly the best meter for reading temperature here. Yeah, it's about 50 degrees centigrade, so it's probably got a ways to go, but it's yeah, as it's warming up now, you can see it's starting to cause problems with the output. It's fluctuating around a bit now. So if I just back this off a bit, it probably stabilize. So yeah, 3.7 amps. So yeah, it's getting warm, so it's starting to go unstable. So I would imagine that certainly with a 3 amp output load, even from right down at 4 volts right through to 18 volts, it's going to be able to sustain an output voltage that is extremely close to the set point and extremely stable from what I'm seeing so far. So kudos to Richtek for putting together this evaluation board. So far it seems to be working very, very well. I guess the next thing to do now is to hook up a scope and my signal generator and see what it's like for output noise and also transient response.